Welcome to the YouTube channel Command Line. Today in this video we are going to learn about divide and conquer. Divide and conquer is a new strategy or an approach to solve an algorithm. So in the first video of insertion sort we have learned the incremental strategy or incremental approach. When you start learning DSA, most of the time you will try to solve any problem using the incremental approach or the brute force approach. So that will be the thing, naturally it will come into your mind. But that brute force approach will not be the best approach every time. So there are other approaches. If you know those approaches, you will know we can use the new approach, a different approach for a problem. So when you know there are multiple approaches to solve a problem, you can use different approaches and choose the best among them to solve the problem. So in this video we are going to start a second approach, which is divide and conquer, which is little bit it's not very complex. It is one among the simplest approaches, but it is little complex than the incremental approach. Let's go into the video and start learning that. This is agenda for today's video. First we will learn what is divide and conquer technique. And then second, we will take one example of divide and conquer, which is nothing but merge sort. Merge sort is one among the common sort. This is one of the best sorts available for sorting given numbers, and that is following divide and conquer. Then we will see how we can able to analyze divide and conquer algorithms. So we have seen how to calculate order of growth and runtime for incremental approach algorithms in the previous video and insertion sort. Today we will see how we can able to identify and analyze the divide and conquer algorithms. At the end, we will use the method we learned to analyze the merge sort algorithm to calculate its order of growth. Let's go into the video. Divide and conquer algorithms mostly use a recursive approach. Recursive approach you might have already known. It is nothing but you will solve the problem, like you will have a problem and you have a function to solve the problem. Now you will divide the problem into multiple, or else you will use the same function to solve a subproblem of that. Somehow you will reduce the scope of the given problem and call the same function to solve the reduced scope of the problem. We cannot call that to infinite times. That's why we have to somehow reduce the scope of the problem and then call the same function. So it will reach a base case at some point. We will see that in this video. So the steps in divide and conquer algorithms will be 3 steps. The first one will be divide. First, we have to divide the problem into one or more subproblems that are smaller instances of the same problem. We have a problem. Now we have to somehow split the input into subproblems and then use the same function to solve the subproblems. So first we have to divide the given problem into subproblems. That is the first step of divide and conquer. And second step is conquer the subproblems by solving them recursively. So solving them recursively means we are going to use the same function which was supposed to solve the given problem. We will use the same function to solve the subproblems also. Now the final step will be combining the solutions of the subproblem to get the final solution of the given problem. So these are the 3 steps of the divide and conquer. First, we have to divide the problem into one or more subproblems. Then we conquer the subproblems recursively. For each subproblem, we have to use the same function to find the solution. Then we combine the solutions of all the subproblems to get the solution of the final problem. So as I told you, recursive functions we cannot call infinite amount of times. So we should be having one base case. Base case in the sense, when we keep on reducing the scope of the problem will be reduced into a small enough, it will become very small. From that moment onwards, we cannot reduce it much further. We cannot reduce the scope of the problem further. In that case, we will be solving it directly. So we will not use a recursive approach anymore. We will directly solve the problem at that point. Other cases, if the case is not a base case, then obviously it is a recursive case. So when it is a recursive case, we have to follow the 3 steps which we learned earlier. This is the approach we are going to follow in divide and conquer method. Now let's take a real-time example of divide and conquer method. Merge sort. Merge sort is recursive because the merge sort function, which is going to receive the input array and the starting and ending element of that particular array, will be called in subsequent times. In the recursive call also, we are going to call the same function merge sort with reduced scope. The start and end are going to be different. The array is going to be same. We will see that in a moment. And the steps here are the divide step. First, we have the subarray at the first call, it will not be a subarray, it will be the complete array of 0 to n. So, but we have to think in the subarray manner, because anytime the function is being called, what we are going to do. So that's why it is mentioned as subarray. The subarray from start to end to be sorted, we have to split that into two adjacent subarrays. So it means we have a full array. Now we are going to divide that into two. So how we can divide the given array into two? So like we have n number of elements, just divide that into half, and then the first element to the mid is the first subarray, and the next element from the mid to the rightmost is the second subarray. So that's why we calculate the mid by adding start and end divided by 2, and then we divide the two subarrays like a of start to mid and a of mid plus 1 to end. Then we conquer. So now we have two subarrays. We have to find solution for both subarray, and we are going to call the same merge sort function with the new start and end. So we call the merge sort function not with 0 and end, this time start and mid, and the second call for the same merge sort will be mid plus 1 and end. Now we conquer the subproblems using the same function recursively. And the final step, the combining the sorted subarrays. So the expectation is once the merge sort call returns, the subarray which was passed to that merge sort is sorted. Now we have two sorted subarrays, a of start to mid and then a of mid plus 1 to end. Now we are going to combine them together into a of start to end to get the final solution. So we have followed the same technique which we learnt in divide and conquer for solving the merge sort. So merge sort is a sorting algorithm which follows divide and conquer approach. So what is the base case here in the merge sort? When the subarray is having just one element, so we are going to keep on splitting the array into two. Like we have like n number of elements. In the first call, we are going to divide into two subarrays, n by 2 and n by 2. And in the second call, like it is going to be n by 4 of 4. And then subsequently it is like n by 8 of 8. So we are going to keep on dividing the given input elements until we reach there is just only one element in a subarray. So when there is only one element in a subarray, we are obviously knowing that that subarray is sorted. There is only one element, there's nothing to compare, that subarray is sorted. So that is the base case. So in the merge sort base case scenario, we don't need to do anything else. So we can simply return the subarray. So the subarray is already sorted. When you reach the base case, return from there. That's all. And what is a recursive case? Whichever is not base case. So it means whenever the subarray is having more than one element, it is a recursive case. When the subarray is not having more than n elements, divide that into 2 and then call the merge sort for both subarrays. This is the code for the merge sort. The first part, we are going to check whether it is a base case. So base case is we have to see like whether that has only one element. When there is only one element in the sorted subarray, the start and end will be same. So when sort and end are same, we can simply return. So we don't need to do any operations there. The base case is simple in merge sort. Second is the recursive case. When it is a recursive case, first we have to divide into two subproblems. So to divide, we need to find the mid. Finding the mid is start plus n divided by 2. It is a floor division in Python. That's why we have two slashes. So floor division means like when you divide 5 by 2, you won't get 2.5. You will get just 2. When you divide 7, you will get 3. So we divide that, we get the midpoint, and then we call the merge sort with new subarrays. First time merge sort a of start to mid, and then second time mid plus 1 to end. So two subarrays we got, and then we call merge sort. So when we reach the merge, we know that the subarrays a of start to mid and a of mid plus 1 to end are already sorted. So we pass that to the merge, and merge will actually merge both subarrays into a single subarray of a of start to end, and then it will give the final solution. This is the merge sort code. Here the missing point is what the merge function is going to do, because merge sort function is already the code is there. We are going to call the same code again and again. So the only missing point is merge. We will see that in the next slide. In the merge sort, we got an input subarray A, and with the position start, mid and end. It is an adjacent subarray, right? It is not like somewhere random places. So it means if we know the start and mid and end, we can assume the first subarray is start to the mid and the second subarray is mid plus 1 to the end. So it means we have a single array. The first half is sorted, the second half is sorted. Now we got to somehow combine both subarrays into a subarray where the full elements are sorted. Yeah, the A of start to mid is sorted. A of mid plus 1 to end is sorted. Now the result what we are expecting is A of start to end should be sorted. Now let's see the merge function in action with an example.
Here, for the merge function, two sorted subarrays are given. Let's call the array as A, and the first subarray is from start to mid, and second subarray is mid plus 1 to end. So as you can see, from start to mid, the first subarray 2, 6, 2, 4, 6, 7 is sorted. Similarly, the second subarray mid plus 1 to end 1, 2, 3, 4 is also sorted. Now we have to merge it into a single array where all the elements in that are sorted. So for that, let's create two arrays and copy the left subarray and right subarray. Let's create two subarrays, left and right. So I'm copying the values from the left subarray 2, 4, 6, 7. This is the left subarray, and the right subarray goes like this: 1, 2, 3, 4. Now, as the values are copied, we are going to replace the existing value in the main subarray itself. So let's consider the main subarray as become empty, as we have removed all the values from the main subarray. So now we are having 8 empty places. Now the comparison starts with I and j. Let's take the first element of, this is the right subarray. So let's assign the first index of both left and right subarray as I and j. This is I and this is j, and the first index in the A is k. Let's start with comparing I and j. 2 and 1. 1 is smaller, so we are copying the value 1 from right subarray to the index k. As we have copied from right subarray, we increment j into j plus 1. So j points to second subarray. Similarly, k becomes k plus 1, k points to second index in array A. Now again compare I and j, 2 and 2. So both are same. Let's copy from the left subarray. As we have copied from the left subarray, let's increment I into I plus 1. Now I is pointing to the second index. And then as usual, similarly increment k to k plus 1, k goes to the third index. So after copying, let's increment k into k plus 1, k goes to the fourth index. Now again comparing I and j. So 4 is greater than 3. So let's copy from right subarray. Increment j and increment k also. Now again compare I and j. 4 and 4 both are same. Let's copy from left subarray. As we have copied from left subarray, increment I. Now I becomes the third index. K also gets increments. K is pointing to sixth index. Compare I and j. J is smaller. Copy from j. Now j has become len of right plus 1. It means j has already crossed the right's last element. So we have no more elements in right subarray. So from this point, let's copy all the elements remaining in the left subarray. So k increments to the seventh element. I is pointing to third element in the left subarray. That is coming to seventh index in the A. 6. Increment I. Increment k. And again copy the last value from the left subarray to the last value in the array A. So this becomes 7. K becomes the length of A. K equal to len of A plus 1. So far now we have copied all the elements from left subarray and right subarray. We compared one by one and then filled the A. So at the end, if you see the array A, all the elements here are sorted: 1, 2, 2, 3, 4, 4, 6, 7. This is how the merge function works.
So the example was clear, we understood what is the concept, and here this is the code for the merge sort. You can see we start initially like we have a input subarray, like two subarrays, A of start to mid and mid to end. Now we have to create two subarrays left and right, and we are copying the given subarrays into left and right because we are going to overwrite the initial subarray A. So we need to copy the content first, and then we initialize two variables I and j equal to 0, and then k is start because we are going to fill the array A from start to end, not from 0 to n. Like it should be start and end. That's why we start k from start. Now as we have seen in the example, first we have to compare. We have to take one element at a time. Like I is going to be pointing to the left subarray's elements and j is going to be pointing to the right array sub elements. So whenever we are going to compare those two elements, whichever is actually smaller, we will take the element and put that into the main array A, and then we will increment the corresponding pointer. I should be less than the left subarray's length and j should be less than the right subarray's length. So in this case, we compare both left of I and right of j, whichever is smaller. We fill that into A of k, and then we increment the corresponding subarray's pointer. Then obviously we have to increment k because next time we have to fill the next element in the array A, right? So we are incrementing k. We will keep doing it until one subarray among left and right gets exhausted. Either I passes the length of left or j passes the length of right. When j passes the length of right, now we have still elements in I. We have still elements in left. So it means we have to keep copying every element from the left. We have to start from the current ith index and then copy everything into A of k. So as long as I is less than length of left, copy that element, increment I and increment k. Similarly, if left subarray is exhausted, it means I has crossed the length of left, then we copy everything from the right subarray from element j until j becomes like all the elements in right subarray gets exhausted. Now let's run this code in VS Code and see how it is performing. Now we are at the interesting section of this video. So we have learned what is divide and conquer approach, and then we have seen a very interesting problem of merge sort which is following the divide and conquer approach. Now we have to see how to analyze any divide and conquer algorithm. So we have seen in the previous chapter that we want to analyze any algorithm, we want to find the runtime, and then we want to find the order of growth of the algorithm so that we can choose the right algorithm for the right situation. Otherwise there will be waste of resources like compute power, time, money, lots of things. So we need to analyze any algorithm, then only we can compare that with other candidates. So now we will see how to analyze any divide and conquer algorithm, and then we will see how to analyze the merge sort. This is the basic formula for any divide and conquer algorithm. The first half is theta of 1, which is for the base case. So in the merge sort case, the base case is when the number of elements in the array becomes 1. It means it becomes less than 2. So in any divide and conquer algorithm, the base case will be reached when the input length or the subproblem is less than some constant number. So we take the constant number as n0. So the first half of the formula says when we reach the base case, the order of growth is 1. It means when we reach the base case in the merge sort, we don't do anything, like we simply return. But in other divide and conquer algorithms, we may take some steps, we may do some calculations in that case. But the point is, whatever the calculation we are going to do, it is going to be same for all the base cases. We may have many subproblems, but each are having the input length less than the constant n0. We are going to run those steps all the subproblems, so it is again going to be constant for the given input. That's why we take the base case as theta of 1. Now the interesting part comes here. So what is the runtime for the recursive case? So when we didn't reach the base case, what we have to do? First we have to divide. So the time taken for divide is d of n, and then next we have to calculate the subproblems. We have to conquer the subproblem. To conquer the subproblems, it takes a times t of n by b. In the case of merge sort, we divide n by 2 and then we got two subproblems. So here both a and b are 2. But it doesn't need to be same for all the problems. So some divide and conquer algorithms where we may divide the given problem into a subproblems, but the input length for each subproblem will be n by b. It doesn't need to be n by every time. There may be overlaps, or there may be like we may leave some numbers. We will see those algorithms in the future, but there is a possibility when we divide the given problem into a subproblems, the input length of each subproblem doesn't need to be n by a. It can be some other number also, so that we take it as n by b. That's why to conquer the runtime of all the subproblems, we have a subproblems, and each subproblem is going to take t of n by b time. That's why the conquer step is going to take a times t of n by b. So at last we have to do the combine step. Combine step is going to produce the n length of output, so that we are saying it is going to be c of n. Let's do the analysis of merge sort. So anyway, base case is going to be same for all the divide and conquer algorithms. For all the divide and conquer algorithms, the base case is going to be just theta of 1. We can just leave it aside. Now we have to calculate the order of growth or runtime for only for the recursive case. For the merge sort, the divide step takes just order of 1, because we just find the average of given input number. So we have the start and end of the array, and we take the average, we get the midpoint. Once we get the midpoint, the divide step is over, because we are just simply going to call the subarray to the next function. That comes under the conquer step. As I said, we are going to simply compute the midpoint. And the second step, to combine, we have like a times t of n by b. In the merge sort case, we are just dividing the given input length into 2, and we get 2 subproblems. So a and b both are 2. So in that case, 2 times t of n by 2. And at last, how much amount of time it is going to take to merge the two subproblems, which is c of n, which we didn't calculate it. We'll calculate it in the next slide. We just take it as c of n now. This is the merge sort program which we have seen earlier in this video. There are 3 while loops. The first while loop is going to run until one of the subarrays is going to get exhausted. The remaining 2 while loops, among the 2 while loops, only one among them is going to run, and that is going to run for the remaining elements in the non-exhausted element. So it means we are going to run the while loop. We are going to run the operations, whatever is going to be run inside the while loop will run for n time. It will not run more than n time or less than n time. It is going to run for n time. And what are the operations we are going to do in the n time? In the first while loop, there is going to be 2 comparison, I and j with the corresponding arrays, and then there is going to be one assignment, which is a of k from either left or right based on the condition, and then there are going to be 2 increments. Either we increment I or j, and then we increment k. So in the first while loop is going to be 2 comparison, 1 assignment and 2 increments. If you go to the other while loops, there is going to be only one among them is going to run, 1 comparison, 1 assignment, 2 increments. So we can say like 2 comparison, 1 comparison not a big deal. That's why we can say that as like one cumulative operation, and that cumulative operation is going to run for n times. So we can say the merge function takes O of n time when the input length is n. Input length means the combined length of both subarray. So when the both subarray input length is n, we can say the merge is taking theta of n time. So the order of growth for merge function is n. So as I said, we have just one execution unit, which is having 1 or 2 comparisons based on the while loop getting executed, and then 1 assignment, which is a of k either from left of I or right of j, and then 2 increments, either I or j and then k. So number of executions n minus start, which is nothing but the input length, total length of the input. So we have taken n, and we can say when we consider the input length is n, and the order of growth for this particular function is theta of n. Now let's try to calculate the runtime for the entire merge sort. We have seen the divide step is taking just O of 1 time, and then we have to calculate. So there is no other loop or operation in the merge sort. Then we just call the merge sort, and then we just go to the combine step, the merge step. So now we have to identify the combined runtime for merging all the sub elements, all the subarrays, and then we have to see how many times we are going to run the merge function. This is order of function calling in the merge sort. When the first time merge sort is called, it is being called with n elements. Then we call merge sort of n by 2 and n by 2, and then we call the merge function for 2 subarrays n by, which are each length n by 2. So the first time, the overall runtime for this particular call sequence is theta of n. And in the second time, so we called merge sort for 2 subarrays n by 2, and that is again going to call merge sort for two subarrays n by 4 and n by 4. Again we are going to combine two subarrays each length n by 4 and n by 4. So there it means you add both n by 4 and n by 4, we get n by 2. So the runtime for solving one sub element here is 1 by 2, and then when we do it for two times, because we do it for two subarrays, it becomes n by, sorry I mentioned it wrongly here, it is again n by 2. So add two n by 2s. In the second step also, to solve all the subarrays, it is taking theta of n time. Similarly, in the third time, we have called merge sort with n by 4 elements in a subarray, and we have called it 4 times. So each time it is going to divide n by 4 into n by 8, and then it is going to call the merge. So this is done for 4 times, and each time the order of growth for merge is theta of n by 4. You add n by 4 for 4 times, you get theta of n. We keep doing it until we reach the base case. The base case is when the subarray length is 1. We have seen in our previous video that if we keep splitting the given number into 2 and then until we reach n, how many times we'll be doing? We'll be doing it for log n times. I have given the video link in the description. Please watch it if you don't know how to calculate log n, why log is answer here. So we do these operations log n plus 1 time because the number of division step happens log n time, and then we do 1 time extra for the first time when merge sort is being called. That's why we do log n plus 1 time. So we can say adding a constant is negligible. In that case, like we can say it is log n times. We are doing an operation whose order of growth is theta of n for log n times. So the entire merge sort, the order of growth is theta of log n time n. So we can say it is theta of n log n. This is how we arrived at the order of growth for merge sort. We have reached the end of the video. So we have learned what is divide and conquer approach. So we have learned already the incremental approach, and we learned another approach of divide and conquer now. And then so the divide and conquer approach has 3 steps: divide and then conquer all the subproblems, and we get the solution for all the subproblems. Then we combine the solutions of each subproblem into the final solution for the given main subproblem. The divide and conquer will be having 2 cases: the base case where we simply go and solve the problem, we will not try to do anything recursive. The non-base case, which is a recursive case, where we split the problem into multiple subproblems and then we call the same function to solve each subproblem. Then we have taken one prime example, which is nothing but merge sort. Merge sort has 2 functions. One is merge sort, another one is merge. And at the second half of the video, we started learning how to analyze any divide and conquer algorithm. Then we used the method to analyze the runtime and order of growth for merge sort, and we arrived at theta of n log n. Hope this video was useful to you. Please let me know if you have any doubts, and please mention in the comment that I have to change something in this video, I have to make it better. If I'm going very fast or very slow, please let me know in the comment, and please ask me any questions in the comment. I'm happy to help you. Thank you for watching. We'll see you soon.